5, chapter 1. We're looking at the limit as a function. So in class, as we looked at section 4, and we're finding the slopes of each of those 2 points that we find, we got closer and closer. So we had some x value that they were giving us. Okay, so like this kind of says, so values of x near 2. So just like those one things, we're getting closer and closer to 2. So sometimes we're getting closer on this side, and sometimes we're getting closer on this side. And those also gave us a y value, right? Let's see if I can draw a better one. So here's a value of 2, and we're getting closer, right? And we're getting closer here. And those same values, so we might have a y value that gave us for 2. So we had a y value as well. So we had some y value for this x of 2. And we were looking at these other x's value that we get closer to it, and those also gave us some y values, right? They gave us some other y values. And then we're asked to find the slope in between each one of those, right? We're asked to find the slope of, say, that one, then we're asked to find the slope of this one, then we're asked to find the slope of this one, and then asked to find the slope of this one, and then average those, right? So this is kind of the idea of the limit. As we approach this value of x, what does that, what is our slopes, as we talked about before, what is our slopes approaching? So not necessarily kind of, we'll look at also what is the y value approaching as well. But we were kind of talking about in class what that slope is approaching. What's the slope getting closer and closer to? What number is it getting closer and closer to? And that's kind of the idea of limit. As we approach, as we get closer and closer to this x value, what is either our y value, our slope, or what are we approaching? What number are we approaching when we either plug in a formula or something like that? So we're going to go ahead and look at this equation, x squared minus x plus 2, and see what values we have when we get near 2. So this one is just looking for what are the y values approaching, where our examples and our problems in the section 4 was looking for the slope. So here's a chart of different x's. So you start off with your x, and then you plug it into that equation, and here are your y's, here's an x, here's your y. So what we're doing is we're going from below 2, and we're getting closer and closer to 2. And kind of like here, if we add the, so here's 2, and we're getting closer on this side. This is the one to the left. And then we're above 2 and approaching it downward, so we're getting closer and closer to 2 on the other side. And we're seeing what those y values get closer and closer to. So like I said, we were using these y values in order to then calculate slope in our section 4. But here we're just looking at what is the y values approach. So here's probably a better looking graph. So as we approach those x values too, what is our y values approaching? Because sometimes we might have in our graphs, there might be a hole here, and maybe we actually have a point up here, and there's a hole there. So we kind of want to know, okay, what is this y value approaching, even though it might not hit it, because maybe there's some other point that it's actually defined as. And so that's kind of the idea of a limit, is as we get closer and closer to one thing, what is either our y's or what is our slope approaching? What is something else approaching? So then we can see that if we look at both these, as we get closer and closer to that x, so we get closer and closer to the x, our y values are getting closer and closer to 4. And we could keep on going, add zeros in there or whatever, but we can see that it's really getting closer and closer to 4. So the limit notation is just a way to say that exact thing. As we approach a certain x, our y value, for the last example, gets closer and closer to something. So that is defined as a limit. So as x approaches some value of x, we label it a because sometimes it changes, not always the same. Our f of a, meaning when my y value, gets closer and closer to some number, L. So as the limit of f of x, so this is in words, the limit of f of x as x gets closer to a. closer to A. The limit of f of x equals L. So before this was, in our last example, we had the m here because we were looking for slope. We were looking for what's the limit of the slope as x approaches a certain letter. So you can do this for different equations. So you could do this for something like if we had the graphs like this, we could say find the limit as x approaches 1 of this equation, x minus 1 over the quantity x squared minus 1. So it might be, as you can see, if we put in 1 down here, I would get 0 on bottom, so I can't plug in 1, nor can I plug in negative 1. So at this point of say this is 1, I have a hole there, right, because it's undefined at that point. But maybe my equation is f of x equals x minus 1 over x squared minus 1. And then I have some kind of domain restrictions, or maybe a piecewise function. So maybe it's defined on that, except for let x equal, say, 2 when x is negative 1. So I labeled my domain. So there it is in my domain, but I'm still going to have a hole, and then I would have this point down here because I defined it that way. So sometimes you might have holes with a point defined, or maybe you just have holes if you just have an equation like that, where then you have your domain restrictions. Or you might actually have a value at A, kind of like our example. We just had x squared. It was just quadratic, right? We actually did have a value of, when I plugged in our A of 2, we did have a y value, right? So sometimes that is defined, sometimes it has a hole in it, but it is defined somewhere else, and sometimes we're just left with a hole. So in those certain circumstances, we can find out, in all three of these, we can find out as the graph goes, and we look at our x values approaching some value of A, some x value, our y values are also approaching some number. So our y values are also approaching some number. And that's what the idea of a limit is. So you go ahead and try this one and try to guess it as we get closer and closer to 1. What is this value going to be? And remember, when we do plug in 1, we get undefined. So that's why we can't just plug in 1. Sometimes if it was a 2, then yeah, we could just plug in 2 and get that number. That's the one where it just went like this, where it was defined at that point. This one might look like there's a hole here and just a hole. And so go ahead and you could try this. But here's how we're going to do it. We're just going to get closer and closer to those values of 1. So I'm going to go below, say like 0.999, and maybe above and go 1.001. And we're going to plug those into this equation and see what the y value is. And then whatever that, and I can get closer and closer, 9999 and 1.0001. So really these are they're kind of easy. Like I have a table here, I think. So I could do each one of these and see what it gets closer to, or I can just really go to, a farther out decimal place on it and see what value it approaches. And as we can see, it's approaching a half. So, I mean, you can do all these in between and figure out the y values, or you can kind of just jump straight down here. And then we look at the idea of just a one-handed limit. So just a one-handed limit is just looking at as we approach from one side. So as you get from one side, what is that y value approaching? So what value am I approaching just from one side? So that equation kind of looks like the same as x approaches A, and from the left is a negative. This is supposed to be an arrow, and that's ugly. So this is from the left or below. F of A equals L. And then we have from the right, That'd be a plus. So left is a negative, right's a plus. And so we could instead we could approach it from above or above. And what's that graph doing from above? Because sometimes you might have a graph that goes like this, and then maybe it goes like this. So it might go to two different numbers. But if it goes to the same number, if these two are both the same number, then the limit as x approaches a, just overall, is that same whatever that value is, that same value. So if those two are the same, then the limit does exist. The limit exists. If it doesn't, kind of like this graph, if it goes to there on that point and down here, then the limit does not exist if they're not the same. So we'll use this one kind of a lot if we talk about infinite limits as we go on. This one will come up quite a bit because as we approach, these are some ugly looking drawings, but as we approach 0, when I have 1 over x, as I get closer and closer to 0, I'm going to have some kind of decimal like 0.001 or, point, 001, 009, something like that. Or negative 0.001 or 0.001, and I can keep on expanding that. What you'll see is this grows, this gets bigger and bigger and bigger, because really this is like 1/100th or 1/1000, negative 1/1000th. And so that just becomes, when I take 1 divided by that, that's just going to be 1,000 or negative 1,000. So I see as I approach 0, if anything with 1 over x or 1 over x squared or 1 over x cubed, that this is going to go on to infinity or negative infinity, based on if I'm going from the left or if I'm going from the right. So, and then we'll check out some of the other ones. So that's kind of an infinite one because it keeps on growing and growing and growing. And then other ones are as x approaches infinity, as x approaches negative infinity. Those are some infinite limits. So that's the kind of idea of an infinite limit, is as we approach that a value, either from the left, from the right, or overall, our graph is keep on growing, growing, growing to positive infinity or going down negative, and keeps on going.